Hi all, welcome to new class. Today's class is about design of asynchronous counters. To design an asynchronous counter, first write the counting sequence, then tabulate the values of reset signal R. So reset signal R for various states of the counter. So first write the counting sequence, then tabulate the values of reset signal R, then obtain the minimal expression for this R value using K-map or any other method, and provide a feedback such that this R or R bar reset all the flip-flops after the desired count. So this reset value is designed to reset all the flip-flops after the desired count. Let us do an example. Design and implement a Mod-6 asynchronous counter using T flip-flop. So this is Mod-6 asynchronous counter. Mod-6 means it has 6 stable state, and that stable states are 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, then 1, 0, 1. So when the sixth clock pulse, that is when 1, 1, 0, that is sixth clock pulse is applied, the counter temporarily goes to this 110 state, but we have to reset this to 000. For that we use this feedback signal. That is, for that we use this reset signal that we have provided. And this is Mod-6 asynchronous counter, that is, we can say divide by 6 counter, because it divide the input clock frequency by 6. So we can call it as divide by 6 counter or Mod-6 asynchronous counter. And here it requires 3 flip-flops. So to design a Mod-6 asynchronous counter, first of all we have to write the counting sequence, that is, write the truth table. So for writing truth table, let Q3, Q2 and Q1 are the 3 outputs of the 3 flip-flops. Then clock pulses. Then the value for R. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. Next is 1, 1, 0. When that is, this is first 1, 0, then 1, 2, 3, 4, 5, 6. So this is the sixth clock pulse. When sixth clock pulse comes, we have to reset the value to 0, 0, 0, 0. So we have to count like 0, 1, 2, 3, 4, 5, again 0, 1, 2, 3, like that. For that when the sixth clock pulse comes, we have to reset these two values to 0. Then only we get the first value 0, 0, 0. So here 0, 0, 0, 0, 0, 0, 1. That is, this R value for this state, that is 1, 1, 0 should be 1. Now we can draw the logic diagram. The question is to design using T flip-flop, and that flip-flop should be in toggle mode. So to get to the toggle mode, what will be the value for this T input? It should be 1. That is, the T flip-flop in 1. That is, T flip-flop with input 1 is in toggle mode. Now this Q1, this is a negative edge triggered T flip-flop. So Q1 output of the first flip-flop is given to the clock input of the second flip-flop. Then Q2 output of the second flip-flop is given to the clock input of the third flip-flop. Now when and Q1, Q2, Q3 are the outputs. So when 1, 1, 0, that is when sixth pulse comes, we have to reset the flip-flop. That is when the output 1, 1, 0, that is this 1, 1, we have to reset. So here we should use a NAND gate. That is these two outputs Q2 and Q3. These two outputs we have to reset when 1, 1 comes. That is, this is R. So we get this is R bar, and this reset value should be, that is, this should be cleared. So here we can use the clear inputs. So we have to clear this. So this is the logic diagram for the Mod 6 asynchronous counter. So when the first clock pulse is given at the negative going edge, it will toggle. That is, Q1 changes to 0 first. Q1 is 0 first. When first clock pulse is applied at the negative going edge, it changes to 1. So this flip-flop will not react. Then again this also will not react. So it will be 0, 0, 1. And after the second clock pulse, again this Q1 toggles. That is 1 changes to 0. Then when 0 comes here, then here the Q2 output toggles. Like that it will react. Let us go for another example. Design and implement a Mod 10 asynchronous counter using T flip-flop. So this is a Mod 10 asynchronous counter. So here the counting is like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then again 0, 1, etc. So when the 10th clock pulse is applied, we have to reset the value. That is 10 is 1010. So we have to reset both these values. So first of all, write the truth table. So this is the truth table, and here we require 4 flip-flops. So these Q4, Q3, Q2 and Q1 are the 4 outputs of the 4 flip-flops. After the 9th clock, that is when the 10th clock pulse is applied, it is 1010. We have to reset this value to 0, 0, 0, 0, 0. So that is the design we have to done here. Now let us draw the logic diagram. So this is again the T flip-flop. So the T input should be in toggle mode, that is 1. Now this is a negative edge triggered flip-flop. So there are 4 flip-flops. The Q1 output of the first flip-flop is given to the clock input of the second flip-flop. Then Q2 output of the second flip-flop is given to the clock input of the third flip-flop. Q3 output of the third flip-flop is given to the clock input of the fourth flip-flop. Then Q1, Q2, Q3, Q4 are the 4 outputs, and Q4 is the MSB and Q1 is the LSB. So here when the 10th clock pulse, that is 1010, 10 means this is 1, 1, 0, 1, 0. So we have to reset these two values of 1, 1. That is when 1010 comes, we have to reset the flip-flops, all the flip-flops. So for that, Q4 output and Q2 output, that is 1, 1. Here 1, 1 comes when Q4 and Q2 are 1. That is 10th clock pulse is, when 10th clock pulse is applied, Q4 and Q2 are 1. So we have to reset that value. So for that we use a NAND gate here. Q4 and Q2. Q2 we have to clear. So use a NAND gate here, and that is cleared. For that we use clear inputs. This is R bar. So in this way we are counting this mod 10 asynchronous counter. That is when the 10th clock pulse is applied, we have to clear all the flip-flops. For that we use this clear input. And this clear input is also called asynchronous input, and it is used to reset the flip-flops. Thank you for watching the class. If you like the classes, please like, share with your friends and subscribe my channel.